Derivatives of polynomials and natural exponential functions, Level 1. In order to find the derivative of polynomials and natural exponential functions without consistently using the definition of the derivative, we need to develop rules that enable us to calculate the derivative with relative ease. Let's start with our first rule, the derivative of a constant function. Recall that the derivative can be geometrically interpreted as the slope of the tangent line to the curve y equals f of x at a given point. If we were to graph a general constant function of the form f of x equals c, where c is a constant, it would look like this. Notice that the constant function is actually a horizontal line. This means that it has no slope. In other words, it has a slope of 0. Since the geometric definition of the derivative is the slope of the tangent line at every given point on the curve, we can conclude that the derivative of a constant function is equal to 0. Alright, let's proceed with our next rule. The second derivative rule is called the power rule. This rule is perfect to take derivatives of power functions of the form f of x equals x raised to the power of n. The rule states that the derivative of a power function whose exponent is n is equal to n times the power function raised to the power of n minus 1. Notice that you have to bring down the exponent and subtract 1 from the original exponent, which then becomes the new exponent of the new function. For example, say that we have the graph f of x equals x. The function is a power function of degree 1. In other words, it's a linear function that passes through the origin, and whose slope of the tangent line at every single point on the curve is equal to 1. This means that the derivative of the function should be equal to 1. Let's use the power rule to show just that. So using the operator d over dx to represent the derivative, we apply it to the function f of x equals x. So we go ahead and apply the power rule. We first bring down 1 and multiply it by x raised to the power of 1 minus 1, which simplifies to x raised to the power of 0. This expression simplifies to 1. So the derivative of f of x equals x is equal to 1. Alright, let's move along to our next rule. The next derivative rule we have in our arsenal is a derivative of a natural exponential function. Let's compute the derivative of a natural exponential function f of x equals e raised to the power of x by using the definition of the derivative. Recall that the definition of the derivative was equal to the following expression. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Using the natural exponential function as our f of x, we go ahead and substitute it into the definition as follows. Next, we go ahead and rewrite this expression as e raised to the power of x times e raised to the power of h by applying the properties of exponents. Next, we go ahead and factor out the common e raised to the power of x term as follows. So now we have e raised to the power of x times the limit as h approaches 0 of the quantity e raised to the power of h minus 1 over h. Notice that we can't just substitute 0 for h, since division by 0 is undefined. So we're going to find this limit in a different way. Notice that this expression does not contain the independent variable x. The only way that this can occur is if the variable x was equal to 0. Recall that any number raised to the power of 0 is equal to 1. This means that this expression is essentially the derivative of the natural exponential function evaluated at x equals 0. As a proof, let's confirm this by finding an expression of the derivative of the natural exponential function evaluated at x equals 0. Doing that, we have the following. Recall that anything raised to the power of 0 is equal to 1. In the end, we obtain the following expression. Now that we know that this limit represents the derivative at x equals 0, we can substitute this limit with f prime of 0. This way, the final derivative of the natural exponential function is equal to e raised to the power of x times f prime of 0. Recall that we can also interpret the derivative of a function as a rate of change. This expression says that the rate of change of a natural exponential function is proportional to the function itself, where the constant of proportion is equal to f prime of 0. In other words, the slope of the tangent line at x equals 0. So let's take a look at the graph and see if we can find a value for f prime of 0. Here we have a graph of the natural exponential function. Now, in order to compute the derivative, by using the expression we derive, we need to find the tangent line to the curve at x equals 0. That is to say, at the point 0, 1. The tangent line through the point 0, 1 is represented by the green line. So looking at the green line, it looks awfully familiar. It looks like the line y equals x, or f of x equals x. So graphing this line on the graph, we see that the tangent line and the line f of x equals x are actually parallel. This means that both lines have the same slope. The slope on the line f of x equals x is 1, so the slope of this tangent line is also 1. This means that the derivative, or f prime of 0, is equal to 1. Substituting this result to the expression we derived earlier, we conclude that the derivative of a natural exponential function is equal to itself. This is by far one of the easiest derivatives that you can find in calculus. Alright, now let's go over a couple of examples and see these rules in action. Let's try the first example. Find the derivative of f of x equals 10. Notice that we are dealing with a constant function, so we need to use the rule for the derivative of a constant function. So applying the rule, we have that the derivative of f of x equals 10 is equal to 0. The derivative of a constant is always equal to 0, because the slope of the tangent line at every given point on the curve is equal to 0. Alright, that was pretty easy. Let's try the next example. Find the derivative of f of x equals x cubed. Notice that we're dealing with a power function of degree 3. So this is a perfect candidate for the power rule. So we go ahead and apply the power rule to the function. Here, the value of n is equal to 3. So we drop down the 3 and multiply it by the function raised to the power of 3 minus 1. Remember, we need to subtract 1 for the exponent. Simplifying the expression, we have that the derivative is equal to 3x squared. Okay, that was also pretty easy. Now let's try one that is slightly more complicated. Find the derivative of f of x equals 1 over x squared. At first, it seems that we can't use any of the rules that we just learned to find the derivative of this function. It turns out that we actually can, but not in its current form. We need to rewrite the function into a derivative-friendly form. Recall from your studies of Algebra 1 that we can rewrite this rational expression as a negative exponent. So we can rewrite this function as x raised to the power of negative 2. This way, we have it in a derivative-friendly form. Now we can apply the power rule. So we bring down the negative 2 and multiply it by x raised to the power of negative 2 minus 1. Notice that we are actually adding two negative numbers, so be careful. Simplifying the expression, we have that the derivative of the function is going to be equal to negative 2 over x cubed. Alright, let's try the next example. Find the derivative of f of x equals the square root of x. Once again, it seems that we don't have a derivative rule that we can use. Just like the previous problem, we need to rewrite this function into a derivative-friendly form. We accomplish this by remembering that radical expressions can be written as fractional powers, as follows. So now we can apply the power rule. So we go ahead and bring down 1/2 and multiply it by x raised to the power of 1/2 minus 1. I hope you remember how to subtract fractions. This is precisely what we need to do now. The way we subtract or add fractions is to have a common denominator, and then subtract or add the numerators, and keeping the common denominator. So doing that, we have the following expression. So it turns out that the derivative is equal to 1 over 2 times the square root of x. Alright, let's try the last example. Find the derivative of f of x equals e raised to the power of x. If you were paying attention, this is one of the easiest derivatives you can compute in calculus. The derivative of a natural exponential function is just equal to itself. And there you go, we are done. Alright, in our next video, we will learn even more derivative rules to help us compute more complicated derivatives. Derivatives of polynomials and natural exponential functions, Level 2. In the previous video, we learned 3 differentiation rules that helped us find a derivative of polynomials and natural exponential functions with relative ease. In this video, we will add even more differentiation rules to our arsenal to find a derivative of slightly more complicated functions. Our next differentiation rule is called the constant multiple rule. The derivative of a constant times a function is a constant times the derivative of the function. In other words, constants can be factored out of the differentiation process, even if the constant appears in the denominator. Geometrically, we can interpret this rule as follows. Say you have a random function, y equals f of x, and then let's say that you multiply this function by a factor of 3. Recall that you can interpret this operation as a transformation. In this case, the product will stretch the graph vertically by a factor of 3. This transformation also affects the slope of the tangent line. In this case, the change in y, also known as a rise, will be tripled, but the change in x, or run, will remain the same. This means that the slope of the tangent line will be tripled. Hence, the constant multiple rule. Alright, let's move along to our next rule, the sum rule. This rule states that the derivative of a sum of functions is the sum of the derivatives. In other words, you take the derivative of each function one by one. The sum rule can also be denoted by using prime notation as follows. The quantity f plus g prime equals f prime plus g prime. Another rule that is very similar to the sum rule is a difference rule. Just like the sum rule, this rule states that when you're taking the derivative of two functions that are being subtracted from one another, you take the derivative of each individual function. Using prime notation, we can denote the difference rule as follows. The quantity f minus g prime equals f prime minus g prime. These rules can be extended to 3, 4, or more finite number of functions. For instance, if you needed to find the derivative of a sum and/or difference of functions, all you need to do is to systematically take the derivative of each function one by one. Alright, now that we are familiar with these new rules, we can now combine them with the derivative of a constant, the power rule, and the derivative of a natural exponential function to differentiate slightly more complicated functions. Let's go over some examples and see this in action. Find the derivative of v as a function of r equals 4/3 pi r cubed. Notice that this function has the constant 4/3 pi, and it also contains a power function of degree 3. In order to find the derivative of this function, we need to use two distinct rules. We're going to use the constant multiple rule and the power rule. We first apply the constant multiple rule by separating the constant and multiplying it by the derivative of r cubed. Now, in order to find the derivative of r cubed, we need to use the power rule. Applying the power rule results in the following expression, 3r squared. Now it is just a matter of simplifying the expression. In this case, the 3's cancel out, resulting in the final answer equal to 4 pi r squared. Notice that in this example, we had to use two distinct rules. In this case, the constant multiple rule and the power rule. Alright, let's try the next example. Find the derivative of f of x equals 5x minus 1. Here we have a difference of two functions. This means that we need to apply the difference rule and take the derivative of each function individually. The first function contains the constant 5 and a power function of degree 1. So the derivative of this function will be equal to 5 after applying the constant multiple rule and power rule. The second function is a constant. Recall from the previous video that the derivative of a constant is equal to 0. So the final derivative of this function is equal to 5. Alright, let's try an example that contains three functions. Find the derivative of g of x equals 5x raised to the power of 8 minus 2x raised to the power of 5 plus 6. In this example, we are face to face with a trinomial. We have three different terms separated by addition and subtraction operators. For this problem, we need to apply a combination of the sum and difference rule, and take derivatives of each term separately. The derivative of the first term and second term require an application of the constant multiple rule. Applying it yields the following expressions. From here, we need to apply the power rule to the first and second term, because they contain power functions of degree 8 and 5 respectively. Applying the power rule yields the following expressions. The last term is just a constant, so the derivative of that function is going to be equal to 0. So the final derivative of this function is equal to 40x raised to the power of 7 minus 10x raised to the power of 4. Alright, let's try the final example. Find the derivative of f of t equals the square root of t minus 1 over the square root of t plus e to the t over 3. Notice that this function has a combination of power functions and natural exponential functions. Before we find the derivative, let's rewrite the radical expressions into a derivative-friendly form. Once we have written the expressions using fractional powers, we go ahead and apply the sum and difference rule to find the derivative of each term. The first and second term requires an application of the power rule. The last term has the constant 1/3, so we go ahead and apply the constant multiple rule, followed by the derivative of the natural exponential function. Taking the derivative of the first term results in the following expression. The derivative of the second term is equal to the following expression. And the derivative of the last term is equal to e raised to the power of t, because the derivative of a natural exponential function is just equal to itself. Simplifying the expressions, we have that the final derivative is equal to 1 over 2 times the square root of t plus 1 over 2 times the square root of t cubed plus e to the t over 3. Alright, in our next and final video on this topic, we will go over more challenging examples that require us to algebraically rewrite functions before we compute their derivatives. Derivatives of polynomials and natural exponential functions, Level 3. Alright, at this point, you should be familiar with the following derivative rules. The derivative of a constant function, the constant multiple rule, the sum and difference rule, the power rule, and the derivative of a natural exponential function. Keep in mind that understanding and knowing how to use these rules is not enough to find a derivative of simple polynomials and natural exponential functions. At times, algebraic techniques learned from your previous math classes need to be implemented in order to manipulate and rewrite functions into a derivative-friendly form. Let's see this in action and jump straight into the first example. Find the derivative of f of x equals the quantity 5x raised to the power of 2. Notice that in this function, we have the quantity 5x being raised to the power of 2. We cannot apply the power rule in its current form. In a much later video, we will learn a new rule that will help us deal with these types of functions more efficiently. For now, with our current differentiation rules at our disposal, we would first need to rewrite the function by applying the power to the constant 5 and the linear function x as follows. Now we are free to apply the constant multiple rule along with the power rule. Applying both rules yields the following expression, 50x. This example illustrates the importance of understanding algebra for the purpose of rewriting functions into a derivative-friendly form before applying specific differentiation rules. Alright, let's try the next example. Find the derivative of f of x equals x times the square root of x. Alright, notice that we have a product of a linear function and a radical function. At first glance, it seems that it would be impossible to find the derivative with the current rules learned from the previous videos. Taking a closer look at the function and recalling that radical functions can be rewritten into fractional powers, we can actually simplify this function into a derivative-friendly form. the radical function can be rewritten as x raised to the power of 1/2. Also notice that you can think of the linear function as x raised to the power of 1. So in essence, we can simplify this expression as follows. X raised to the power of 3/2. Now we have a function written into a derivative-friendly form. All that is left to do is to apply the power rule as follows, resulting in the final expression equal to 3 times the square root of x over 2. Always be on the lookout for ways to rewrite the function into a derivative-friendly form before attempting to compute the derivative. Alright, let's move along to the next example. Find the derivative of f of x equals the quantity x squared plus x plus 3 all over x. Like the previous example, this function seems very complicated, and you might feel that you do not have a specific rule that you can apply to find the derivative. Let's see if we can first rewrite this function into a derivative-friendly form before we give up. Recall that you can think of division as another form of multiplication. In this case, you can think of the numerator being multiplied by the expression 1 over x as follows. Viewing the function in this way, we can see that we can actually distribute this expression to each of the terms in the numerator as follows. Then we go ahead and simplify each term, obtaining the following derivative-friendly function. F of x equals x plus 1 plus 3x raised to the power of -1. Now it is just a matter of applying the sum rule and apply the power rule to the first and third term. We also need to apply the derivative of a constant function to the second term, as follows. Lastly, we go ahead and rewrite the expression, obtaining the final derivative, which is equal to 1 minus 3 over x squared. Once again, always try to rewrite the function into a derivative-friendly form. Alright, let's try the next example. Find the derivative of f of x equals the quantity x squared plus 4x plus 3 all over the fifth root of x squared. This function is similar to the last example. The only difference is that now we have a radical expression in the denominator. Just like the previous example, we need to distribute this radical expression to all the terms in the numerator. Before we do that, let's rewrite the radical expression by using fractional powers, as follows. Next, we go ahead and divide each term in the numerator by this expression. In order to simplify each term, we're going to have to subtract the exponents of each term, as follows. Simplifying each term, we obtain the following derivative-friendly form. Now it is just a matter of using the sum rule and the constant multiple rule to each of the terms. We also need to use the power rule and also apply it to each of the terms. Doing that, we obtain the following. Lastly, you can simplify the expression by rewriting the fractional powers into radical expressions, obtaining the final derivative, which is equal to 8 times the fifth root of x cubed over 5 plus 12 over 5 times the fifth root of x squared minus 6 over 5 times the fifth root of x to the power of 7. It is key that you rewrite functions into derivative-friendly forms before you attempt to find the derivative of the function. Alright, let's go over the final example. Find the derivative of f of x equals the quantity x plus 3 times the quantity x squared minus 5x plus 2. Alright, this function is a product of a binomial and a trinomial. It seems that it is impossible to find the derivative of this function with our current differentiation rules. Similar to the previous examples, we need to rewrite this expression into a derivative-friendly form, for which we can then apply one or more of the derivative rules learned so far. For this particular problem, we can rewrite this expression by distributing the binomial to the trinomial. So we take the first term of the binomial and multiply it by each of the terms of the trinomial. Then we do the same for the second term of the binomial. From here, it is just a matter of simplifying the expression by collecting like terms. Doing that, we obtain the following expression. Now that we have a derivative-friendly form, we now apply the sum and difference rule, constant multiple rule, and power rule to the respective terms. Applying these rules yields the final derivative, which is equal to
3x squared minus 4x minus 13. Alright, now that we know how to use simple differentiation rules, we are ready to learn even more rules. In our next video, we will learn the product rule and learn how to apply it to find the derivative of slightly more complicated functions.